Hello, this is Dr. Joe Chow speaking regarding this PAMPA dissolution. I would like to make some introduction about this product. This instrumentation was invented most recently about 2 years. And in terms of its application, it's really can be used in B prediction. Uh, B means like bioequivalency. I think everybody recognize that. In addition to this bioequivalence prediction, it can be used in terms of 505B2 because 505B2 actually they are uh, measuring these Cmax and AUC parameters. So all these two parameters, AUC and Cmax, can be really easily predict using this instrumentation. Okay, and the accuracy wise is pretty high. Okay, so today we will give some typical example about the B prediction. All right, so let's come to this PPT. Here's my uh, writer about previous job experience in Sandoz, where I do this generic drug R&D. And in Pfizer, I did the new drug analytical research. Yet, I've about 5 years experience in New Jersey Institute of Tech as adjunct professor. Okay, so all these, are just my background, uh, introduction. Okay, now comes to this important figure regarding the human GI tract pH. Well, in terms of this GI tract pH wise is why is that important? The whole graph was the NIH published this graph. What that says to us is that our pH change with respect to time wise in small bowel and large bowel, and how the pH was changed with respect to time. So you can see more or less like in the about beginning 30 minutes or so, that means when the drug is our stomach, the pH is around 1.6. It's not traditionally think 1.2. Okay, so it got to be 1.6. And then after 30 minutes, you can see this pH suddenly increase. Okay, that means soon after 30 minutes, you can measure the pH increase to around 6.5. Okay, on average, that can last until about 2 hours. Okay, around this region. So therefore, by knowing this pH change from stomach to small intestine, we think that two segment, right? The first segment is stomach for pH about 1.6, and the upper small intestine is about pH 6.5. So with this measurement along this human GI tract, therefore we design a dissolution according to whatever found per NIH graph, right? Okay, so as you see from this figure, is so-called PAMPA dissolution. This dissolution, everybody understand, is on the upper part. There are 6 vessels. Yet on the lower portion is also 6 PAMPA vessel corresponding to this dissolution vessel. So in the middle, there is a pump. So like we just described, all the media is according to the pH we just mentioned. However, the median composition is not buffer. We are using a so-called biorelevant media to mimic this human GI tract composition. Okay, so if you are using buffer, you really deviate from this human GI media. Okay, so therefore, this biorelevant media is used in this vessel for dissolving the tablet or capsule. Okay, so over here initially we do 400 ml, roughly 400 ml, all of the gastric fluid. Okay, and that lasts for 30 minutes. And from 30 minutes and beyond, we will add the small intestine fluid to make sure the final volume becomes like 500. Okay, so that will more or less, in terms of pH, mimic to human GI tract, so as to this volume wise. Okay, so the palm here is used to pump the drug dissolved in the biorelevant media and pump through this line to the so-called PAMPA. And you can see from these figures, these the blue area represent the dissolution media, right? And then the drug inside the blue area will be penetrate to the pink area, which is the plasma. And there is a so-called fiber optics that was really here to measure the amount of drug penetrated respect to time, right? So both parameter, one is the permeation and the other parameter is dissolution. They are both recorded through the fiber optics to the PC. So respect to time, okay? So that these two parameter really is correspondingly to the IVIVC model. Yet this IVC model is really validated 30 years ago through a bunch of scientists. So we understand that CP is from dissolution, PE is from this permeation. So we know we can, control these two parameters well, and therefore, you can mimic this GI tract, right, by placing the your reference drug into 1, 2, 3 vessel, and your test drug into 4, 5, 6 vessel. So they are, parallelly compared, and therefore you will know eventually through the program comparison, you can know how good is your test drug versus reference drug are, right? Okay, so by using such a design, we will be able to generate some, these bioequivalence data, right? So we can check it out. The first case is telmistan 40 milligram test under PAMPA for the B prediction. As you can see, the telmistan 40 milligram was used in determining these bioequivalent, and you will see the red line represent myocarditis 40 milligram. The blue line represent the generic drug called Fosun 40 milligram. And dissolution wise, as you can see, they are pretty close, from each other. However, the permeation wise, as you can see, the red line is actually myocarditis, and the blue line is Fosun product. So from this comparison of the slope, okay, which is like maybe starting this fourth point and on, because these permeation start increasing, right? So you can see all these red dots can be regressed versus the blue dots can also be regressed. Once they are done the regression, there must be a slope. So by comparison, the slope from T to R, you can get a slope ratio. And what that slope ratio really represent is a Cmax. Why is that? Because you will see the y-axis of the penetration plot is amount absorbed, right? And then here x-axis is amount is the time, right? So if you have y divided by x, that's amount absorbed per unit time. That is slope, and that is your slope of, let's say, blue to red. So you will get a slope ratio, right? So that slope ratio really tell us how close of test product to reference product. Now, in this case, it's 93% for fluorescence, okay? And further calculation for this AUC-wise is error ratio to predict AUC. Then we use error ratio of area under curve of test and these mitotics. Okay, so this area under red and area under blue line, starting from 50 minutes, can be calculated the ratio wise about 93%. Okay, so from these two calculations shown on the graph, then we can confirm that these Cmax AUC is going to pass. But actually it is, because they are really the approval drug in the market. Okay, so these tell us that the machine can predict precisely about the generic drug performance. So it's quite useful using such a tool to predict your generic drug performance. That will save a lot of time and money-wise, right? And in addition to that, if the blue line as a generic drug is deviate from the red one, right? Then you can see how much deviation it is, and therefore you can use that as your information for making reformulation, and that will bring your blue as close as possible to the red line, which is the RLD, the reference drug. Okay, so basically that's the case one B prediction, and maybe we will introduce more like in terms of B criteria. Like we just said, there are two criteria, right? So what you can do from the graph generated through the PAMPA dissolution, you want to make slope comparison, and you want to make area comparison for T and R. Okay, so the requirement is usually for within that range. It's 80 to 120%. Okay, if your test is like very close to 100%, that means your test drug or formulation is pretty good, right? Okay, so let's look at this second case example. Is ezetimibe 10 milligram, PAMPA BE. Let's check it out. From this outcome, you can see the left side dissolution, right side permeation. Especially from the right side permeation, you can tell the red one is the RLD, and blue one is Sandoz. Just by looking, by eye, the slope-wise, they are pretty close from Sandoz to Ezetrol. Actually, after done the calculation, we come up with about 98%. And about AUC, as we know, the area under the red and under the blue, starting 50 and up, can be calculated, and that come up with about 90%. So both, within 80 to 120%, and the B prediction is successful. right? Because both drugs are really approved in the market already. Okay, this machine will give us very simple and straightforward time-saving way of prediction instead of like using this like pilot bio traditional way cost money and time and not accurate. Okay, so maybe we will check it out the next case which is for the Vosaton 80 milligram PAMPA. The result shown as the PP says here. If you have a red, which is like Codiovan, blue is Sandoz drug, and the black is the T drug from China. And then you can see the blue and red, they are fairly close in terms of permeation. Yet the black one is lag behind, especially in the acid region. In acid, Vosaton penetrate faster. As you can see, within only 20 minutes, it raised drastically. So beyond the force point, which is like as we know, they are in the region of pH 6.5, and yet the penetration rate becomes like plateau. Okay, so it's very interesting if you are doing such a high permeation in acid drug wise, you need to have this machine having the permeation measurement capability. Therefore, you can tell that your drug is it close to the red or is it far away like this, right? So it's very interesting and very powerful tool in the laboratory, can precisely predict the bioequivalence. All right, let's check it out. The last one, which is the etoricoxib 60 milligram. In this case, we see the result like this. In this case, you can barely see the difference between like the brand Akosia versus Atol, which is the generic drug. But then there are two lines. One is red, one is blue. They are almost identical. They are overlapping. So that according to this CMAX and AUC, well, for sure they are going to be like nearby 100%. And in fact, it is. I mean, both are approved drug in the market, right? So what the system tells is the same. Up to this case, we studied already 4 cases. We understand that system can tell exactly what's going on about your generic version formulation. Whenever it passes, it will show like this, right? Or, closer to the red. Whenever it deviates, it will show just like the previous one we saw, right? The black line for the Vosaton, is way off, right? So that means like this is a quite unique and very powerful machine that will help us resolve the scientific headache for not only generic drug R&D people, and also can help these 505(b)(2) drug developer, and also to the new drug developing also, right? Okay, let's check it out about how these performance of machines P value compared to the clinical study value for each of the drug. Here we have 1, 2, 3, 4, 5, 6 drug. That's the PAMPA value. That's the human clinical value. And as you can see, for each of them, they are fairly close. They are fairly close. Okay, so that means like this system, can really help us out in terms of creating the P value. Okay, and from this PPT, what we want to say is that comparison of the traditional way versus nowadays the PAMPA method. As you can see, all these cost-wise or time-wise from traditional way is much higher compared to this nowadays using this PAMPA machine, right? In addition to that is that even if you done the traditional pilot bio study through 10 subjects, what the data really come up with two variable. One is formation variable, the other one is subject variation. So we have two variable like produced in the same result of BE data. So if the deviation between T and R, there's some obvious deviation wise, you want to do reformulation, right? If it's deviate. But then at this time, then how you going to tell the formulation effect or the subject variation effect? It will be very difficult to tell. So in this case, you will end up with guessing, right? But then you might end up with like failing again, right? Okay. So, but I mean, we can do it more scientific way is just by using the PAMPA, dissolution. So in this case, this PAMPA dissolution really just exclude the subject variation, right? Just purely the machine comparison, the RLD versus test. So the only variation that will show on the the graph as we just saw is the formulation variation. So even the formulation variation having the parameter detected, so you can do easy reformulation, right? So this is a much more convenient and more scientific way in doing the drug formulation, right? Okay. So to make a like final conclusion wise comparison of these three methods in terms of B prediction wise. The first method we just talked, and then this IVIC method, I think some people might use it already using the software to do the B prediction. Okay, and third method is PAMPA method. As you can see from the table, the cost wise, is like lot difference in between the three methods, and in fact, in terms of B prediction, right? This PAMPA method is much higher because it has proven this IVIC model for everybody to follow, and therefore it's precise in terms of doing this dissolution and permeation in a simultaneous way. Okay, so that the machine major really follow the formula that was validated. So that means that whatever data generated is really the difference in between two formulation. Okay, so it's very interesting way in doing this PAMPA method. Not only that, these data can also be used to do the reformulation because you have CB and BE major. If there's a difference, exceeding your expectation, then you can do reformulation easily. Not only that, the PAMPA data can also be applied, in Bio5B2 formulation design. Okay, these are the so many like interesting things can be found by using this special so-called PAMPA dissolution instrumentation. Okay, all right. To make like a summarization about its application, it can not only used in generic drug bioequivalent study can also apply to this 505(b)(2 the Cmax AUC prediction because it has ILD also, right? Doing the 505(b)(2. Yet in NDA application, well, we all know definitely there's no ILD. So how are you going to predict the absorption? There is a way. There is a way. There is a way that we can, soon after animal study, we can use the data from animal study plus ADME approval database with PAMPA dissolution. This human clinical PK, can be predict through whatever these three items that can, help us in doing the NDA prediction. Okay. So all in all, the PAMPA dissolution really is a very powerful tool today because it just came out maybe in 2 years or so. And I hope that everybody can really study in this area that might help your drug development, right? And I will stop here. If you have any question, then you can, either email me or, call me. Doesn't matter. So I will be willing to answer your question. Okay. Anyway, I will stop now. Thank you very much. You have a nice one.